Hello and welcome to the Fourier part of this classical mechanics course. In this part of the course we'll be learning Fourier theory, and that'll involve quite a lot of maths. But after we've got that out of the way, we'll have some fun applying Fourier techniques to all kinds of different physical problems and understanding physics from a Fourier perspective. And this will help with all the other parts of the course as well, where we can apply these Fourier techniques to different parts of the course. Now, in this short video, what I want to do is give you an example of a place where you're probably already thinking about things from a Fourier perspective, and just to point this out so you can see sort of where this is headed. The example I want to give, or the first example I want to give, is an audio spectrum. So here is a sound. If you listen to that closely, you'll hear that it sounds like maybe a couple of different frequencies beating together and giving us a kind of a beat note, because you can hear the sound sort of being modulated. Now, one of the things that Fourier techniques allow me to do is take this function of time, because this audio signal is the sound pressure as a function of time. I can take that signal as recorded by a microphone and convert it into a frequency spectrum. I can calculate what frequencies there are in that audio signal. And so here is the audio spectrum. The vertical axis here is the power, so it's the power that exists in each frequency, and the units here are arbitrary. And we can see there's this little bump here, which is of no consequence. The frequencies really here are concentrated in something just above 500 Hertz, and there are a few different frequencies in here that are beating together to give us the sound of this whistle. And so this spectrum is something that you're probably used to thinking about. Maybe you've seen the graphic equalizers in audio playback software, where you can change the amount of bass that you have and the amount of treble that you have. Well, that's just taking an audio signal and breaking it up into different frequencies, and then amplifying some parts of the spectrum and de-amplifying other parts. And the human ear can hear between 20 Hertz and about 20 kilohertz, and so this sound here falls in about 500 Hertz, which is well within the bandwidth we expect the human ear to be able to hear. And so this is the audio spectrum, and a Fourier transform, Fourier theory, allows us to take a signal of time and calculate which frequencies exist in this audio spectrum. One thing that's important to realize here is if I had an audio spectrum with just a pure sine wave, then I would get a single spike here, because a pure sine wave has a single frequency in it. And so a single frequency sine wave will give me a spike here of a single frequency. The fact that I have some distribution of frequencies here tells me that I don't have a pure sine wave note in my audio spectrum. Okay, here's another example. This is an example of light, so an electromagnetic spectrum. This is the spectrum of sunlight. The yellow curve is the sunlight that hits the top of our atmosphere. The red is what makes it through the atmosphere, and so some wavelengths are absorbed. So the x-axis here now is a wavelength, which is like the inverse of frequency, but it's basically the same physical quantity on the x-axis, just a different scale. The vertical axis again is in some sort of power, telling you how much power you have at each frequency. And so we see that some frequencies make it quite well through the atmosphere. So in the visible part here, where our eyes work, there's a lot of power. Over here, around 1300 nanometers, water absorbs pretty much all of the light and nothing makes it through the atmosphere. And so we're probably used to thinking about a spectrum, like we take white light and we can break it up into its different colors, making rainbows with prisms or diffraction gratings. And so we know that light is made up of different colors, different frequencies, and this is just a graph telling us how much of each different frequency we have. Now, if you think about electromagnetic waves, it's a wave just the same way that an audio signal is a wave, and if you had that waveform, if you could measure it somehow, which is very difficult to do, but if you could take this waveform as a function of time and then calculate this spectrum by doing a Fourier transform. So a Fourier transform takes a function of time or space and turns it into a function of frequency, or in this case, wavelength. So here's an example of something that I did using a Fourier transform. Here's the time series of this whistle again, just the first quarter of a second of that signal. It goes on for longer, but it's just the first quarter of a second so that you can actually see the wiggles here. And you can see it's got a strong sine wave component. It's just wiggling up and down here. And it's modulated. As we've discussed, there are a few different frequencies in here that beat together to give us a beat pattern. And so I can take this signal, I can do Fourier theory on it, and I can calculate the spectrum, and we see that the different frequencies are bunched up here just above 500 Hertz. Now in this example, the time series is close to a pure sine wave, but not quite, and that's why all the frequencies here it's nearly a single frequency, and it's all bunched up together, but there is some distribution of frequencies. And I want to note here as well that the spectrum that we're looking at here does not care about the phase of the waves. If I took a few different sine waves here and added them together to try and replicate this curve here, if I changed the relative phase of these waves, I would change the shape of this curve. The spectrum doesn't care about the phase, it only cares about the amplitude of each different frequency. And when I say frequency, I mean how much of a particular frequency sine wave I have. Okay, so here's a summary. In both these examples, we start with some waveform as a function of time, or it could be a function of space. In the case of the sun, we have some electromagnetic wave arriving at Earth, and it has some amplitude as a function of time. Same with the acoustic wave, it arrives at our ears, and this wave has some amplitude as a function of time. But we can think about this waveform, which has a function of time, we can think about this as being made up of a whole bunch of different frequencies, and then ask how much of each frequency do we have. And the spectrum shows us which frequencies, or wavelengths, make up the light or the sound. And so this is a Fourier way of thinking about things. Instead of thinking about what the waveform in time looks like, I can say, well, what does it look like in frequency? So this is the Fourier way of thinking about things. So Fourier theory allows us to calculate such a spectrum, and that is really just the beginning. And as I mentioned, one thing is that the spectrum doesn't take into account the phase of all the different frequencies that go into our waveform. So much more than just the spectrum, Fourier theory will take care of the phase of all the different frequency components, and in general, this is a kind of, I hope, a succinct statement of what Fourier theory can do. It takes any waveform in time or space, and you can uniquely express this waveform as a sum over different frequencies with the correct phase and amplitude. So for any different waveform or shape in time or space, you can write that down as a sum of different frequencies with the right phase and amplitude, and then draw a graph of what the amplitude of all and phases of all these different frequencies is. And this graph of amplitude and phase, that's called a Fourier transform. So the next videos will explain, I guess we'll work our way up to how to take a Fourier transform and then explain how powerful Fourier transforms can be in understanding physics.